Okay, so this is a lesson on medians, altitudes, and then we're going to get into how these line up with bisectors and centers of triangles. And then we're also going to look at centers, and we're also going to look at mid segments. Okay, so we've already understand what a perpendicular bisector is and an angle bisector. That was in our last video. We need to get the idea of a median of a triangle. If I have a triangle and I look at the vertex and then I look at the midpoint of the opposite side and I connect them, this is a median. An altitude is very similar. I take the triangle and I start at the vertex, but I make myself perpendicular to the opposite side. That's going to give me an altitude. Okay, so I'm going to do a little bit of constructing using Sketchpad to show you the four centers of a triangle, and we'll kind of work from there. Okay, so what we're going to do is we're going to build four what are called centers of triangles, and they each are formed in a different way, and they each serve a slightly different purpose. Well, three of them do. The fourth one is just completely useless, but we go through it anyway. So the first one I'm going to create is a thing called the Circumcenter. So this will be my sketch of the Circumcenter. I want to build just an ordinary triangle here to kind of work on this. And what the Circumcenter is it's where the three perpendicular bisectors meet. So what I'm going to do is I'm going to find the midpoint for all three of these sides. So we're going to construct the three midpoints. And then we're going to construct perpendicular bisectors. So I want to be perpendicular to that side through that point, perpendicular to this side through that point, and then I want to be perpendicular to this side through this point. Okay, so lo and behold, all of them meet at a single point here. That point is what we call the Circumcenter. Now, the reason why that is, well, we'll kind of get into a couple things here. One, this point is the same distance from all three vertices. So it's the same, it's like 3.09 there. Measure that distance, comes up as 3.09. And we measure that distance. It also, missed something there. There we go. That distance also comes up as 3.09. Why it's called the Circumcenter is that, like, if you grab that point and you build a circle that goes through the three vertices, it is at the center of that circle. So that kind of gives me the idea of the Circumcenter. The Circumcenter is built out of the perpendicular bisectors. So remember, these things go through the midpoint and they are all perpendicular. All right, so that is the Circumcenter. Let's build the next one. The next one is what we're going to call, whoops, that's not what I wanted, is what we're going to call the Incenter. Okay, so in this case, we're going to build the triangle here. Same idea, but now instead of using perpendicular bisectors, we're going to create angle bisectors, right? So I think I can do this all at once. If I grab all three lines and say construct, nope, gotta do it two at a time. So two of the lines construct an angle don't do that. Construct an angle bisector. So let's go 2. Construct the angle bisector. There's one of them. There's 2. Okay, so lo and behold, again, all of these points line up at the same point, and that's what we call the incenter. So all of these are a result of bisecting angles, right? So what we note here is like these two angles are equal, these two angles are equal, and these two angles, not that one, these two angles will also be equal. So there we go. So we've got three angle bisectors. What is true here is that if I pick a side and I pick a point and I measure that distance, the distance from the center to the sides are always the same. And same for the third side. They're all 1.15 or 1.51 centimeters here. So why is it called the incenter? Well, last time if I stretched a circle out to the three vertices, it fit all three. Here, if I stretch the circle to the sides, it will do that. And so that circle is tangent to all three sides. And the incenter is the center of the circle inside the triangle. All right, so there's our drawing of the incenter. Okay, so we have two more centers to look at. The next one is what's called the centroid. It's kind of a useful one. So earlier we just talked about making medians. Medians go through midpoints, so I'm going to construct the three midpoints here, and then I'm going to build the three medians. So it goes from vertex to midpoint, vertex to midpoint, and vertex to midpoint. And again, they all line up at the same point. So this is what we are going to call the centroid of the triangle. Now, if you were to cut this triangle out of the page and put your finger underneath that centroid, it would balance. That point is actually the center of balance for the triangle. So we'll look at that a little bit more later on, but it's a pretty useful point. So that's three of the centers. And the last one, which is just kind of, we can construct it, but it's fairly not useful, is if we take the three altitudes. So I want to go from vertex to opposite side and construct a perpendicular. So that's one altitude. There is the second altitude. Aha! We're going to notice something here. And we're going to construct the third altitude. And please note that, oops, one too many lines there. Let's do that again. Construct the third altitude. You will note that this center happened to end up outside the triangle. That's completely fine. If I move and make it in an acute triangle, it's going to come inside. If I make it an obtuse triangle, it's outside. So let's put it on the inside for the moment. These are altitudes. So if you look at these angles of intersection, there's 1, 2, 3. They're all going to be labeled as right angles. There we go. There's 1, 2, 3. So this is where the three altitudes meet. We have a name for this. We call this the orthocenter. It really has no practical applications, but ortho meaning right. So it's the center formed by altitudes which form right angles with the sides and go through the vertices. Okay, so four centers of a triangle. The circumcenter from perpendicular bisectors, the incenter from angle bisectors, the centroid from medians, and the orthocenter from altitudes. Okay, so the last topic in this is going to be what we call the mid-segment of a triangle. And to get the mid-segment of a triangle, we have to have a triangle. And we're going to pick the midpoint of two of the sides, and we're going to connect it. And that segment that's going across is what we call the mid-segment. Now, we're going to get a theorem here that's going to say that if this is triangle A, B, C, and this is the mid-segment MN, our theorem is going to say two things. It's going to say that MN is 1/2 of AB, and that MN is parallel to AB. And we want to be able to, so this is what we're going to call the triangle mid-segment theorem. Okay, so how do we actually justify this and prove it? All right, so we know that this is congruent to this is congruent to that. That's what our drawing says. We're actually going to do this in a coordinate way. So I'm going to imagine A being at the origin at 0, 0. We're going to imagine that AB, we just laid it down along the x-axis. So B, the y-coordinate, is also going to be 0. And we're going to carefully say that this point by the ruler postulate is at 2 little a. Now, C, we don't know where it is, but we can describe this point as like 2 little b and 2 little c. Okay, so if I'm thinking about this, and I'm going to go and find the location of M, so the midpoint M should be, take the x's, 0 and 2b, divide that by 2, take the y's, 0 plus 2c, and divide that by 2, puts this at the location BC. So M is at BC. Alright, so where is N? Okay, N, play the same game, right? 2b plus 2a over 2, 2c plus 0 over 2. Let's see, that's going to be, all the 2's wash away. That leaves me with b plus a. I'm going to call that a plus b. 2c plus 0 is just 2c, divided by 2 is c. So this is going to be at a plus b, comma c. All right. So right off the bat, the y value is not changing. It's going from c to c. The x value has gone from a to a plus b. So the distance from m to n should be a plus b minus b, which is just a. And the distance from a to b is 2a minus 0, which is 2a. Let's see, 2a, that's twice the size of mn. So ab is in fact half of ab, right? Half of 2a would be a, so half of ab is mn. So this we have proven. All right. Now, how do we prove that two lines are parallel using coordinates? Well, we show that they have the same slopes. So let's see, what's the slope of mn, right? So what's the slope of mn is going to be y2 minus y1 over x2 minus x1. That's 0 over a, which is just 0. And how about the slope of AB, right? Slope of AB is going to be y2 minus y1 over x2 minus x1. So that's just going to give me 0 over 2a, which works out to be 0. The two slopes are the same, which means that the line segments are in fact parallel, which is the other thing that we needed to prove for the triangle mid-segment theorem. So lots going on here. Medians connecting vertices and midpoints, altitudes connecting vertices to opposite sides so that they're perpendicular, 4 centers of a triangle, circumcenter, incenter, centroid, and orthocenter, and the mid-segment of a triangle, and the fact that it is half the length of the opposite side and parallel to it. All right, that's it.